Okay, so this video is about the three different types of day that astronomers use, which seems like a slightly bizarre concept, but it is important that you know the difference between them. So the basic idea here is that there are three types of day. The first one we call the solar day, and this is like our normal day. The time it takes for the Earth to rotate so the Sun appears to return back to the same position in the sky, remembering that most of the motion of objects in the sky is caused by the Earth's axial rotation. That's it spinning on its axis. Okay, so the first type of day defined to get the Sun back into the same place in the sky. The next type of day, the sidereal day, is the time it takes to get the stars to return back to the same position in the sky. And that works out to be slightly less for reasons we'll talk about in a second. And the final type of day is the lunar day, and that's just the time it takes for the Earth to rotate so the Moon appears to return to the same position in the sky. And it turns out that takes more time. Again, we're going to explain all of these. So what's the reason then that there are different types of day? Well, we're going to look at that, but we must importantly remember that the solar day is the one that we define as 24 hours. That's going to be important later on because it's going to seem a little bit weird. Okay, so why are there three different days? Well, we've said that the main cause of all of these days is the rotation of the Earth, but in addition to the rotation of the Earth spinning on its axis, the other objects involved are moving as well. So the Earth is not only spinning on its axis, it also orbits around the Sun, moving 1/365th roughly of the way around the Sun, which is about a degree around the orbit around the Sun every day. So that's one thing. And the second thing is the Moon is orbiting the Earth. So since the Moon takes about 27 days to complete one orbit, it'll get about 1/27th of the way around its orbit while the Earth is rotating for a single day. And that leads to about an extra 13 degrees of motion of the Moon. And these two things are going to be critical for explaining the different types of day. Okay, so solar day then. Very often people say the solar day or the 24 hours is one complete rotation of the Earth. Well, not quite. We've defined it as the time it takes to get the Sun back in the same position in the sky. So we're going to go and look at this situation here. And it turns out that actually a solar day needs a 361 degree rotation of the Earth. So what you're going to do is imagine you're standing, just for simplicity's sake, on the equator at the position of this red dot, where at the moment the Sun is directly overhead along this green line. So if you look straight up, you would see the Sun. And we're going to run the animation to show what's going to happen for how far we need that red dot to rotate round to get the Sun back overhead again. Now, I've exaggerated the amount of travel of the Earth around its orbit so that you can see the effect. In reality, remember, it's only 1 degree. I'm going to run it and see what happens. So you're standing on the red dot, okay, so sunset now, night time, okay, sunrise again, and we've now rotated back so that the Sun is directly overhead. But if you look at that, that means we've rotated further than 360 degrees. And remember, for the real situation, it's only an extra 1 degree of rotation, but you can clearly see that that's happened, okay? I'm going to run it back one more time so you can see that. Look at the direction the red dot's pointing in. It's kept there on the green line for you, so you've got that for a reference. We've rotated through 360 degrees before we get the Sun back overhead. The 360 degree rotation is about there, and now the Sun's back overhead, okay? So that extra 1 degree of rotation is important. We just need to remember 24 hours then is 361 degrees of rotation, and that's our sort of starting point. If we then look at the sidereal day, the time it takes to get the stars to appear in the same position, then that turns out to be a 360 degree rotation. And the reason is that that tiny amount of 1 degree's motion around the orbital path for the Earth makes very little difference to the direction that stars appear in the sky because the stars are so far away. The Sun is relatively close to us, and so that makes a difference when we look at the Sun. But you can see even on this diagram where the star we're looking at is only about 3 times further away than the Sun, which is ridiculous. The angle is already smaller than that 1 degree angle. I know it's not 1 degree on the diagram again, we've exaggerated it so you can see it. But the angle to the star is much smaller. And as we take that star to a realistic distance, okay, millions of times further away than the Sun is, then that angle will get so small that the extra rotation the Earth will need can be completely ignored. Okay? Completely ignored. Okay, so the angle decreases for more distant stars. Obviously, this is not to scale. So sidereal day is therefore a 360-degree rotation. Now, if you think about it, if the solar day is a 361-degree rotation, and the sidereal day is a 360-degree rotation, then the reason that the sidereal day tends up shorter is just a question of ratios. The Earth's rotated less fast, so it takes less time. How much less time? Well, it's 360/360 of the solar day, right? That's just a ratio issue, okay? When you do the calculation, that gives you a sidereal day length of 23.934 hours. 0.934 hours in minutes is about 56 minutes, so that's the length of the sidereal day. 23 hours, 56 minutes, 4 minutes less than the solar day. If you really want to bang your head against the table with this, you can go and look at the Wikipedia page where they discuss the 4 or 5 different versions of the sidereal day, depending on how really picky you want to be. So, bear in mind, this is still just a slight approximation, but it gives us the correct idea. And the lunar day, the last one. So this turns out to correspond to a roughly 373-degree rotation of the Earth on its axis. And the reason for that is that as the Earth rotates on its axis, as it spins on its axis, the Moon is orbiting around its orbital path in the same direction. So the Moon's orbital motion is in the same direction as the Earth's axial rotation, would be the fancy words we'd use to describe that. So if we run the animation, what you can see happens then is that the red dot, which represents our viewing position, has to rotate further to get the Moon back overhead, because the Moon is moving around its orbit. So one more time, we'll show you that. So we start off with the Moon overhead, red dot there, okay, rotate it round. The Moon is moving around its orbit during our rotation, so we've got to 360 degrees now, and we have to go further. And this is roughly correctly to scale. That's about an extra 13 degrees of rotation, 1/27th of the Moon's motion around its orbit, which turns out to be about 13 degrees. Okay, and again, if we just play the same ratios game, multiply it up, okay, that gives us 24.8 hours. The 0.8 hours is 48 minutes, and that's approximately the 50 minutes that the quoted lunar day is longer than a solar day. Again, we're making some assumptions here in this basic calculation, but it demonstrates the right idea for the reasons that the lunar day is longer. The Earth's got to rotate further to catch up with the extra rotation, or so the extra orbit of the Moon along its orbital path. So those are the 3 different types of day. Key things to take away: you need to know what they're called, you need to know which object is being used as the reference object. So Sun for the solar day, stars for the sidereal day, and the Moon for the lunar day. And you need to know the lengths of those so that you can talk about them sensibly.